All right, recording is rolling. Welcome to Thursday, October 12th. Right, so yesterday we started talking about gravity and orbits. Now this is all part of Unit 3 by AP's book, so it's all going to go on the same quiz, kind of, right? So I'll do a quick review with you guys here at the top. Right as the bell was ringing yesterday, I was starting to show you guys Lagrange points. I have an animation for you guys there. One thing we're going to do in a few minutes is say like a journey to the center of a planet. How does the gravity field change as a function of like how deep you are, right? There's a question on AP Classroom that has to do with scaling, like scale up the size of a planet, like different masses, different radial sizes. How does that change? I forget if they asked like gravity field or orbital speed, something like that. Right? And there's some concepts that are similar to what we'll look here in a few minutes. Right? And then we'll have some time at the end. We'll knock out probably at least a couple of textbook puzzles. You guys know the end of the 9 weeks is today's the last day of the first 9 weeks. Right? So definitely double check, focus, make sure you got everything in that you want in. If there's anything missing or quiz corrections, right? Make sure you get to me before the weekend. Anything you get in the grade tray before the weekend, I can put in the grade book. Right? Anything you guys get to me on Tuesday, well, by then the grade book is locked and there's nothing I can really do. So make sure you get it to me tomorrow. Be all right, today or tomorrow. Right. AP Classroom Unit 3, let's have that due on Tuesday. You guys know we have a 3-day weekend coming up, right? Right? Yeah, all right. So Tuesday we'll go over the solutions. So just have that done by then so we can go over the solutions then. And then a picture retakes tomorrow, if that applies to you. Right? So you guys go, we're done. All right. Actually, one more thing on this list. Here, maybe I'll add it in right here. Is solar eclipse or solar eclipses. So I saw in the news there's a solar eclipse out west in a couple of days, and this page actually printed out a few years ago. It's been one of my infographics hanging outside my door, but it's this band right here across New Mexico. Oh, look at that, 2023. That's this year, October 14th. Hey, that's in 2 days. Right? Yeah, you can see one of these solar eclipses out west. Right? Do you guys remember a solar eclipse a few years ago ran by here? Right? It was actually like right across like Tennessee and South Carolina. So that was it back in 2017. And oh, hey, what's this band right here? This is, let's see a date on this. Yeah, August 12, 2045. So if you guys are still like living in Florida in 2045, then you're gonna see a solar eclipse and you're like, oh yeah, that's right. I remember back in high school, my old physics teacher, he was telling me about this, right? You guys know that, right? And so, yeah, how would astronomers know that like 2045 is going to be the solar eclipse? Oh, well, because they know about orbital mechanics. Yeah, it's like all the stuff that we're doing right now, right? Kepler's laws, Newton's orbits, right? They can plug into a computer program. Go many of you use that in the future. There's a story about Columbus and his crews going. He made a few trips out to the west. I think, if I remember right, he never actually landed on the continent, but a bunch of these islands like down in the Caribbean. And one of his trips, there was a shipwreck, and he had to make it with the natives so they could get supplies while they were waiting for like repairs and help, right? Because they got this wrecked ship. Right? And at some point, the natives are kind of tired of these Spaniards like hanging out in their place, right? They don't want to give them any more food, so they're about to chase them off. Columbus has this almanac with them and opens up and realizes, ooh, hey, there's going to be an eclipse here. If it was solar or lunar, but it's one of the right? And so it goes to the locals. It's like, oh, if you don't feed us more food, I'm gonna let's go with lunar. I think it could have been right. I'm gonna make the moon turn red, right? And then moon turns red, and locals break out and resupply him, and he's able to eventually get back to Spain. Okay. Great. Let's talk about eclipses. Eclipses, because otherwise I don't know another good opportunity to talk about this. Right. You guys probably know the difference between solar eclipse versus a lunar eclipse. Right. What's going on with the solar eclipse? What's the geometry? Yes.
That is moon in between the Earth and Sun.
Yeah, there you go. Right. So like this is obviously not the scale, but right here's the sun and the Earth, and the moon might be somewhere thereabouts, so that the moon casts a shadow on the Earth. Right. That's what happened a few years ago. That's also what each of these are showing. Right. Oh, and speaking of solar eclipses, how many times the diameter is the sun compared to the diameter of the moon? It's about 400 times as big. And by a complete coincidence of geometry, it's also like 400 times further away. What that means is that the angular size of each of these in the sky, from our point of view, looks like the same size, right? Like if you talk to someone like 2,000 years ago, say, what's bigger, the sun or the moon? Like, oh, we're the same size to us, right? And what that means is that when the moon passes right in front of the sun, it can just barely cover it, right? Just barely covers it. or it could. That's actually what all these blue bands are, where the moon is completely covered in sun. What these yellow bands are, because you guys know that orbits aren't exactly circular, kind of close, but not exactly, right? They're more like elliptical, right? Is sometimes uh, the sun and moon, their positions, the moon will have a slightly smaller angular size. So that's probably what's going on in a couple days. So they're like if you're in New Mexico, you'll see like a bright ring around the moon, right, with the sun's like peeking out, something like that, right? Right. So how about a lunar eclipse? What's the geometry going on with a lunar eclipse? The Earth over here. Yeah,
That is the Earth between, the Earth between the moon and the sun.
exactly. All right. So I forgot the moon over here. The Earth is now casting a shadow on the moon, right? This is a more common to see, right? Solar eclipses, you got to be in the right place at the right time. Maybe every few decades you might have a shot to see one of those, right? Right. But yeah, not necessarily, but a lot of times, right? This will see about. Oh yeah, go ahead.
That was my question.
Oh,
Actually. Is
yeah.
every lunar eclipse a new moon?
Yeah, is every lunar eclipse align with the new moon? Well, it would align. So, like, if there is a lunar eclipse, that would align to being a new moon, right? But yeah, not necessarily exactly. So, like, if you look at the orbital planes of like where everything is, yeah, like this is not to scale at all. Like, if the Earth was the size of a basketball, the moon would be about the size of a tennis ball. Maybe like I think it's like 14 or 15 feet away from each other, right? And so you need the orbital planes to like be like flat, right? And if they're not exactly lined up, which depending on like where and when the time of year, they might be a little out of alignment, right? That's all it takes for the Earth shadow to not necessarily fall on the moon. Yeah, so you need like a really kind of special alignment. But this will happen pretty often. I think about every year or so. It's something opportunity, right? You guys have probably seen lunar eclipse, maybe, or if you haven't, then look for the next opportunity. Uh, what does the moon look like? What color does it turn? Red? Yeah, it turns red. Yeah, yeah. If you guys ever see a red moon, you're probably looking at a lunar eclipse. Why red? Why does it turn red? Yeah, longest wavelength of light has to do with, right? So if you look up in the sky, suppose you're like standing here on Earth like midday, you look at the sky, like the sky looks blue, has to do with the sun emits like all different colors of light, but it's like the short wavelengths that get through our atmosphere, like through the thin part of the atmosphere. What about it? Sunrise and sunset? What color is the sky? Ooh, like a red color, right? Because sunrise and sunset, that's a longer part of the atmosphere that has to the sunlight has to go through, and then it turns out the longer wavelengths, like the red colors, end up making it through. Oh, so if you were standing here on the moon during a lunar eclipse, now I bet you would see a ring around the Earth that was red, that was all of Earth's sunrises and sunsets simultaneously. Yeah, that's why the moon turns red during a lunar eclipse. All of Earth's sunrises and sunsets are refracted onto the moon simultaneously. So there you go. So fun trivia. All right, there's eclipses. All right, so quick recap of stuff yesterday. So the story starts with astronomy. People tracking like where the planets exactly in night sky. Right, guy named Tycho Brahe meticulously and precisely tracked like where's Mars every night for like many years, and then Kepler put this together. Okay, planets move in ellipses, not exactly circles. You guys saw why yesterday that's more stable than circles. So about equal areas and equal times. And then this third law is going to come up later today. I think when we pull up the textbook questions, there's one where I'll actually prove this to you guys. Right now, Kepler figured out this proportion, the time period to go around and the average distance to the sun per planet. Right? This squared cube proportional relationship. Right? And then here's the Newtonian update. When you bring in this universal gravitation, right, you can make an exact equation. Right? I'll show you guys why this actually you can derive this with universal gravitation plus centripetal motion, kind of orbital speed kind of concept. Okay? Right, here's universal gravitation. You guys were introduced to yesterday. So force between two objects is okay, it's equal and opposite forces. Earth pulls on the moon, same as much as the moon pulls on the Earth, right? Or you and the Earth. Yeah, yeah, right. Right, so that force is proportional to each mass, right? And okay, so times universal gravity constant, right? And then divided by the distance squared, so that's an inverse square relationship. And that distance, speaking of that distance, guys, is that a surface to surface distance or a center to center distance? Center to center, right? Like a lot of these calculations, we're gonna make believe that the entire mass of the Earth is at a single point right at its own center mass, and then these calculations will work out like this, and they work out fine. Right? Oh, here's so why an inverse square relationship between force and distance? Right? Here's maybe an intuitive version of this, like intensity of light. It has to do with living in three spatial dimensions universe. Right? So if you back up twice as far away, now you're only catching a quarter of the light. 3 times far away, only a ninth of the light. Right? So gravity works the same way. Okay? you can take the answer to your last lab, like centripetal force, and what if that centripetal force is being provided by the gravity, and let's use universal gravitation, right? You can solve for v, and this will tell you orbital speed for a circular orbit. That's what it's going to be, circular orbit. What speed is that going, right? You can do this. I should tell you guys. You guys should be able to do this from scratch. I mean, it's like 3 steps, right? Set up, little algebra, answer. Right? You guys should be able to solve this from scratch. This would be a completely fair AP question for an FRQ. They might say, do something with orbital speed. And they might take this and like do something else with it too. Like find some kind of proportional relationship, right? What if you like have 9 times the mass of a planet or something, right? I think there's a AP classroom question that's kind of similar to that. Right? Escape speed is a similar type set. Now this is for energy conservation, which we haven't quite done yet. That's a simple looking expression. Right? So you put it all together, right? And you get, here we go. So here's this guy standing on Alaska. He sends like some gravity field. Everyone on the surface of there are like 9.8 meters per second squared. And yesterday we ran a calculation to show you like kind of where that comes from. Universal gravity constant. So Von Jelly number 6.67 times 10 to the minus 11. Got some units. Mass of the Earth. Radial size of the Earth. Remember, the distance between you and the Earth from this point of view, like, is the radius of the Earth, right? That is the distance, right? Center mass. Okay. Here's orbital speed, like for a circular orbit, and then here's escape speed, which we'll probably touch back on in a few weeks. We do energy, right? Okay. And then realistically, usually things in orbit are like between these 2 speeds, right? And okay, maybe closer to this one if it's closer to circular orbit. Comets might be kind of closer to this one because highly elliptical. This one you guys saw, eggshell planet. So if there was like an eggshell planet, you could walk around on the surface and the gravity would be pulling you like as if there was a single point mass at the center. But if you dig a hole and go in it, I was showing you guys yesterday, well, everything up down cancels out, but so does everything right and left. So it's like a gravity-free interior inside that hollow planet. Okay, now that might look like an interesting triviality, like, okay, what are we gonna do that? We're actually going to use this later today to say, well, what happens inside a solid planet? And this is going to be part of a proof to figure out what happens to the gravity inside a solid planet. So hold on to the idea. Right, you guys saw tides, right? Close side and far side of the moon. This is one of the few times we'll say, well, Earth's actually 3-dimensional and they're like closer and further away surfaces, right? So we got tides going on. Right? And Lagrange point. Now here's where the bell was about ringing yesterday. So recap this and then show you guys an animation, right, of this in action. Right? So there are these points of sort of gravitational stability, right? Like L1, I think is the most intuitive, right? Sun pulls to the left, Earth pulls to the right. There's some point where it kind of cancels out, sort of, right? Now, when you include also this rotational dynamics, these other ones also pop up. It was James Webb Telescope. That's the one I forgot the name of the other day. It was about a year or 2 back, was launched into space, and it's actually orbiting this L2 point, which is also one of these points that's kind of stable in a rotational context. So Earth and the Sun are both pulling to the left gravitationally. But if you're like along to the right, like following the orbit of Earth, you can watch the Earth like beneath your feet, never actually get any closer to it. So it's L2's first, right? L3, similar type story. Before 1957, before we ever sent anything to space, there was some speculation there might be like some kind of mirror Earth over here. Now we know there isn't, but fun thought anyway. Right? And then L4 and L5 end up being like the most stable of these L points. Right? And yeah, I got an animation for you guys. Ooh, let's go do that. Let me flip the screen over. Oh, yeah. Okay. All right. Let's take a look at, oh, where'd it go? Hold on, let me pause this. All right, so we're back here. All right, so here we go. Here's an animation of, here's our solar system from above, got sun in the middle. Here's the inner planets, where the third one, right? And then, now you guys know the sun is like 99% of the mass of our solar system. It's like dominant, right? And the second biggest mass by far is Jupiter, right? So these two like drive like a lot of the mechanics of our solar system, right? Guys, what's all these pink dots? All these pink dots. Asteroids. That's the asteroid belt, isn't it? Right? Hey, that asteroid belt looks kind of triangular-ish, sort of, right? Guys, oh, because Jupiter here on the opposite side. Hey, that's the L3 point right here for Jupiter and the Sun. You guys see it going around like that corner of the triangle? Okay? There's also some green patches. Those are called the Greek and the Trojan asteroids. And if you make an equilateral triangle between the Sun, the Jupiter, and this green patch, well, that would be an equilateral triangle, right? Like here's like L4 and L5. And those are sort of gravitationally stable. So if an asteroid kind of gets in that vicinity, it tends to want to stay there. It kind of drifts away, it'll sort of kind of drift back. Okay? So there you go. There's L points right there. All right, let's get back over here. Next thing, let's do Journey to the Center of the Earth. Is what we're going to do. Journey to the Center of the Earth. So get a picture going and a graph going. Right, you guys got your notes out for this one? Right? Because maybe a challenge question. I'm wondering if you guys can complete the graph that I'm about to start going here before I show you guys how this finishes out. So I got this guy, surface of the earth. He's got a shovel. He's gonna tunnel down into a planet. So let's do a spiral staircase, like all the way down, right? Maybe in the middle there's like a cave, right? We're gonna make believe it's not all molten and hot down there. So maybe it's just like dirt that goes through like consistent density. We're doing some simplification, just like we normally do in this class, right? Something like that. And at some point, maybe he'll hit all the way down to the center. When he's climbing down the staircase, maybe I'll have him like halfway down here, right? Let's say for completion, like a real big picture. Let's also have him at some other point, like taking off on a rocket, and or maybe I should say like a really tall tower, right? So he's like climbing up like a crazy tall tower, right? And he has a scale with him, so he's like always standing on a scale. He's checking his weight at all these different places. Surface of Earth, top of the tower, halfway down the spiral staircase. He brought it all the way to the center of the planet. Okay? And I want to know sort of like what's his weight as a function of his radial distance from the center, right? So if this is like the center right here, right? Maybe I could have some generic radius r going out, right? And there's a special radial distance, which is the radius of the planet itself. I'll call that capital R, right? Something like that. Right, so let's do this graph. Sometimes I do weight versus radial size. Actually, I'm going to alter that a little bit. Let's do gravity field versus radial distance from the center, because it'll be the same graph shape, right? Just a little bit different units we're thinking in terms of, right? Guys, what's some units for a gravity field? Yeah, meters per second squared is our go-to, right? Sometimes AP switches it up and you see what other unit could use. Newton per kilogram. There you go. Newton per kilogram. Kind of Newton second law motion. They like to sometimes for like gravity fields of planets express them on Newton per kilogram. Right. And then okay, let's go 0 zeros. Your origin right there. I'll put this radial size of Earth is bam. It's right there. It's one special radius. Right. Right. And there's one point that all of us know for sure is going to be on this graph, because all of us have lived our entire lives at the surface. At the surface, the gravity field is like 9.8 meters per second squared. So I can throw that point on the board. Let's go maybe bam, right about there-ish. And then right, this could be like 9.8 meter per second squared, or you could call it 9.8 Newton per kilogram. Okay, so we got 1 point on the board. Okay, right, there we go. All right, next thing. Actually, let's take off on the rocket so we can just finish out everything to the right side of this graph. I'm saying rocket, but maybe he's just climbing crazy tall tower. Maybe there's like a space elevator that goes all the way up to like Mars or something crazy. Right? So he's just going up, up, up. Right? He's looking at the scale reading, or maybe he's feeling, right? Like what's happening to the gravity field. Now, the further away he gets, is that gravity field getting stronger or weaker? Weaker. In fact, if you're all the way to Mars, is the Earth still pulling on you? Maybe a tiny, tiny, tiny bit. It would be negligible at that point, right? It'd be basically zero. So with that in mind, what does this graph look like? Anyway, anything to the right? Anything to the right? Here, I'll do a quick trip around class and see if anybody gets what that shape should ideally look like. Okay? So you're climbing a crazy tall tower. You're just going off into space. Okay? Maybe you're checking your weight. Right? Divide by mass, maybe like a gravity field concept. Okay? What's that? All right. Eli's got it. Okay. I think some of you guys are close. Yeah, okay. So some of you guys got it kind of close. I think Eli got it exactly. Okay. Well, how about a formula? Do you guys remember gravity field is gm on r squared, right? If I throw in another m, now it turns back into gravity force, right? You guys know that? Okay. Oh, hey, we got the answer right here, because constant, universal gravity constant, mass of the planet, that's not changing, right? So do you guys see an inverse square relationship? If you didn't get it before, I bet you can get it now. This G compared to this R, right? Okay. Are you guys thinking some version of this going on? Some version of that, right? Where it would like asymptotically approach zero, right? It asymptotically approaches zero right there. Is that what's going on? Okay, sure. Okay. All right. The next point that I think you guys can probably get is like, if you go right to the center, suppose there's like a cave at the center. How would you feel in the very center? Heavy, light? What do you guys think? Zero gravity. You'd be floating around like an astronaut, right? Okay. Now, one way to think of it is if you split the Earth into like a trillion different points, like every grain of sand is pulling you to say its own way, right? So at the surface, you're pulled all these different ways, but all the left-right cancels out. And so the net effect is you're pulled straight down. Right? But in the center, you're pulled that way, that way, that way, that way, that way, right? It all cancels out, which means you can put what point on this graph? Yeah, 0, 0, right? At 0 distance from the center, that you would experience 0 gravity field, right? 0, 0, right? Right. Now here's the tricky part is what about like descending or climbing the staircase? Like if you're halfway to the center, that's where this guy is right here. See, it's like halfway to the center, like R/2, right? And he's bringing the scale down with him, right? At half the distance to the center, would he have half his weight from the surface, or more than half, or less than half? And that goes hand in hand with how do these dots connect on this graph? Is it a straight shot, or does it kind of curve out like this, or kind of curve out like this? How's it gonna go? Right, so here's where I'm gonna prove this to you guys. Right, you guys ready to stretch your imaginations a little bit? Right, you guys ready for some hard thinking notes here? Right. So I'm gonna start with gravity field is universal gravity constant times mass of the planet divided by radial size squared. I'll use lowercase r for like a variable r because he's like descending the staircase kind of, right? Something like that, right? Oh, but you know what? The mass of a planet and its radial size, those are related to each other. Like if there's a larger volume planet, like with larger radial size, I bet it's also more massive, assuming the same density, right? Right. So these two variables are not necessarily independent from each other. So maybe I could express one in terms of the other and make a little substitution. So I could figure out like, what does gravity field say strictly as a function of r? So something like that, right? So over on the side here, when you think about what kind of substitution I can make, the mass of a planet. Okay, now this might be helpful maybe for some AP questions, possibly on AP Classroom coming up over the weekend. Can you say the mass of something is equal to its density times its volume? Can you guys see that? Here's mass. Here's density. Here's volume. Right? Mass, density, volume. Right? Or sometimes you see this rearranged, like density is mass per unit volume, right? You've got some object, you say, well, I know it's so massive and it takes up so much volume, I divide those two, I can get the density of the material, kind of, right? And one of the simplifications we're going to make is that we got a planet of uniform density, so it's the same density all the way through. Is that exactly true? Well, not really, but we do a lot of simplifications in this class, right? So we're going to say it's just like Earth, dirt, all the way through. Okay. And somehow I'm trying to connect this back to R, right? Back to radius R, right? So here's something else I know, is that volume could be, what's a good formula for volume? How about the simple cube? If it's just a cube, what times what times what? Yeah, length, width, height, right? And if they're all the same, could I just go like R cubed, right? Actually, that right there is all you need. If you just call this proportion, I mean, a planet is not a cube exactly, right? But it would be proportional to that. Do you guys know how to turn this into a sphere? You multiply by, yeah, 4/3 pi. There you go, 4/3 pi. Okay. Right. So put this all together. The mass of the planet is its density times 4/3 pi times r cubed is what that is. Right? Wouldn't that be the case? Right. Right here. Side note here. There was a poster I showed you guys a long time back. I think this goes back to August. You guys remember scaling, right? Whenever you get to this gravitation section, AP likes to ask questions about like, if a planet changes by this factor, how's that affect like something else, like its gravity field, its orbital speed? And sometimes they'll tell you both mass and radial size, but sometimes they'll scale up one and say common density, and you have to keep something like this in mind, right? When you scale something up, now here's a very simple cube, right? But spheres work with the exact same proportions. If you scale something up, say by a factor of 3 in one dimension, and then you do that to all 3 dimensions, different properties will change by different factors because they have different dimensional values. Anything that's linear, length, width, height, perimeter, that's all going to scale it by whatever factor you scale it by. Right? Like in this case, 3 to the power 1 is 3. Okay. But what if you want to paint this thing? Well, that's going to be like 9 times the paint because that's a 2-dimensional concept, right? Factor of 3, but in 2 dimensions, that's like 9 times the paint, 9 times the shadow, right? If you watch a shadow on the ground, this little box compared to this big crate, right? And finally, what if you fill this with water versus filled with water? Right? You guys see maybe like 27 little boxes can fit in the big crate? So it's scale it by factor 3 in 3 dimensions. It's like 27, right? And so that's in terms of volume. And I bet mass occupies volume, so that would also be 27 times the mass, 27 times the weight, and all that, right? Right, so just throw on 4/3 pi, and now you got a sphere, and it's the same thing, right? Right. Let's do a substitution. So I'm going to take this mass value and as a function of radius, I'm going to substitute right there. Going to make a substitution. Okay. Right. So let's go. Gravity field equals universal gravity constant times. Right. I got the density of the planet. I got a 4/3 pi. I got r cubed, and then this is all divided by r squared because of an inverse square relationship. Right, I said. Ooh. Now what? What cancels out? Yeah, a couple of the r's, right? Right. So now the gravity field of the planet is equal to, okay, I got universal gravity constant, I got the density of the dirt it's made out of, I got a 4/3 pi, and then all times just plain r, right? Because r cubed over r squared, that's just r, right? And all right, so here's an important step right here. It's an important step. Okay. Oh, you guys see all this stuff right here? Oops. All this stuff is just constants. Universal gravity constant, the density of the planet we're calling uniform, so that's just some value. Okay? 4/3 and pi, those are just numbers, so that's constant. This is all constants here. Okay? And what that means is that the gravity field is directly proportional to the radial size of the planet. Okay? So if you're comparing two planets side by side, say I got like a small planet, a big planet, and this one has radius r, and this one has exactly double that radius, like 2r. Right? And you stand at the surface of each one, and you try to figure out like what is one guy's weight compared to the other guy's weight. Is it like same mass, or maybe you're comparing gravity fields? I should say comparing gravity fields, right? What is this guy's gravity field on the right compared to the left? It's also twice as much, right? Now this planet has how many times the mass is the big planet compared to the little planet? 8, right? 2 times 2 times 2. This guy's 8 times the mass of this guy. This might have m, and this guy's like 8m, right? No, this guy's so okay. So it looks like this guy's gonna be a lot heavier, maybe 8 times heavier, but he's also twice as far away. Inverse square relationship, 8 divided by 4. Hey, that would be 2 times gravity field, right? 2 times weight, right? Right. Now combine that with here's where I promised you guys this was gonna come back in. Let me find it. Where are you? Aha, there we go. All right, one more detail is gonna pull us all together. And that goes back to this eggshell planet, back to the eggshell. Right? So remember, if you're inside an eggshell, all the gravity above you and elevation cancels out. Right? Maybe anything below you can count, but nothing above you. Right? So let's go back to here we go. Right, this right here. Right? And this guy who's like halfway up the spiral staircase, like between the center and the surface, right? Like little circle right here. Oh, hey, actually, this kind of lines up with the picture I just showed you, right? Where everything above him in elevation is essentially a series of eggshells, isn't it? Eggshell, 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 which all the gravity cancels out, right? So it's as if this guy halfway down is standing on a small planet at half the radius of the original planet. And since we just proved that the gravity field then is proportional to that radius, right? How does that graph finish off? Linear, right? Like this guy halfway down, wouldn't he have half the weight of the guy at the surface? If he dropped to something, he could see 4.9 meters per second squared to be accelerated down. Yeah, so we got this point here, but really any point you could do a linear relationship like that, wouldn't it? Right? In fact, the slope of this, you guys think that slope would be g rho 4/3 pi? Haha, I bet it would be, right? Right, you guys got that too? One of your textbook questions says something very similar to this, but for escape speed. And I gave you guys formula for escape speed, so you can essentially take that and do the same mechanics. And yeah, see if you can solve that one and you do it from scratch, right? Okay, guys, get back. All right, go. Next. Oh, textbook puzzles is what I got next. So we'll knock out at least a couple of textbook puzzles here. All right. So these won't be due for, I haven't actually set a due date, but probably in the next week. I'm thinking maybe next Friday. I think would be pretty good, right? Because remind you guys the organization here. Chapter 7 does the same thing that AP does in Unit 3, which is kind of in 2 halves. Like the first half is like circular motion, centripetal force. And then the second half is gravitation, and then you can put that together and make orbits. I think here, I went over most of these with you guys in class. I'm gonna hit the last two rotational ones real fast, just the setup, just think how they would be set up, right? And then we'll go to answer some gravitation questions. So number 27 looks a lot like your guys' lab. See, there's some mass up here, M1, there's some weight down here. The mass is M2, so the weight would be M2G, right? And then there's a string that goes through a hole in the center of the table, right? And they say a frictionless surface, and they give us some tangential speed. That is pretty well exactly the setup for your last lab, isn't it? So that is, right? And they're saying, what's the tension in the string? What's the horizontal force acting on the puck? What's the speed of the puck? Well, here, you guys have the solutions right now because I posted solutions, but basically that's your lab, isn't it? Right? You just take the formulas from the lab, switch up a force, do mv squared over r, right? Wouldn't the weight down be balanced by the tension up? So the tension is equivalent to this hanging weight, which is m sub 2 times g, right? And the whole thing, right? You do mv squared over r and solve any of those questions, you guys think? Right. And the other one that we hadn't supposedly gone over in class was number 32. There's this roller coaster, right? Goes through this valley, goes over this hill, and there's a couple questions. One is, what is the force of the track, say, down at the bottom of the valley? And the other question is, well, what's the maximum speed of this roller coaster going over the hill? Because if it goes too fast, it might fly off, kind of situation, right? So draw this out. At least want to set up a free body diagram with you guys, and then I think you guys will be able to figure this out from there. So we got the roller coaster kind of deal, right? At some point, the roller coaster is down here at the valley, and at some point later, it's like up here going to the top. And there's some speed associated. So I'll say like the speed at the bottom, maybe up here like maybe the speed at the top, something I think. Right? Do you guys think as it's going up, it's like slowing down? You guys think? Right? Like the higher it goes, the slower it's going. Right? When we get to conservation of energy, we might come back and talk about that. Like so, hold on to that idea. Higher it goes, the slower it's going. Right? So it's speeding up on the way down, so down the way up. Right? Right? At the bottom, you feel really wet, light or heavy? Really heavy, which might indicate something about the normal force on the track, or from the track on the coaster. So, right, center mass dot there. Right? What's forces on this guy at the bottom? It's got a weight down. I call it mg, which by the way, when we get to this guy over here, it'll eventually have the exact same weight on it. Right, mg, the exact same weight. Right? And what about the normal force down here? Is it large or small compared to that weight? Yeah, large. So I'll make it larger. F sub n, normal force. Okay. And what that normal force is has to do with how fast it's going. Like if it's at rest, they would be the same, right? But it's in motion. So if it's going faster, I bet that normal force is larger. And also something to do with this, if you fit a circle like tangent to that part of the track, something to do with like the radial size of that circle, right? Like mv squared over r. I bet you guys can put it all together. Do you guys think the difference between those two forces, the normal force up and the weight down, is the net force, which is the centripetal force? Let me jot that down. Okay. So the net force, or sometimes I write it this way, sum of forces, but you guys know that's the same thing, right? The sum of the forces is the net force, right? Could you guys say is the centripetal force in this case? Right? Okay. And then what about the top here? Do you think you feel light or heavy up here? Probably kind of light, right? And I bet the faster it's going, the lighter you feel. So I'll draw a normal force, but I'll make it kind of small. That's a small normal force up there, right? Normal force is like support force from the surface, right? Do you guys think if you went too fast, that normal force could shrink all the way to zero? At which point the coaster's like, wow, flying off the track. Ooh, right? And I bet that has to do with how fast you're going, and also what is this circle has some radial size you could fit tangent to that, right? Has something to do with that. Okay. So here, I'll leave you guys with that, and I think that you guys can figure out the answers to those questions from that setup. Right? All right, let's do a gravitation question. Number 37. Objects with masses, let's say 200 grams, or 200 kilograms, 500 kilograms, separated by a distance of so many meters. Find the net gravity force exerted on a 50 kilogram object placed midway between them. Right? And then follow-up question: at what position, other than infinitely far away, would the gravity effectively be zero? It sounds kind of like the L1 point, like a Lagrange type of process, right? So something like that. Right. So let's go ahead and solve this one. 37. Right. This one's a pretty straightforward fundamental gravity type question. Okay. Look at let's have a line between these two masses. So 200 kilograms of 500 kilograms. Here, I'll just call it M left and M right. How about that? Okay. So I have the mass on the left and a different mass on the right. Okay. And they're separated by some distance. Separated by some distance, right? Maybe I'll, they told you a number here. I'll solve in terms of variables. How about that? Let's call it D, right? And they said, what's the gravity force on an object that has some mass C that's at the midpoint? And midpoint would be right in the middle, right? So I'll call this guy mass C, right? It's equidistant. It's like half a D and half a D, okay? Right? And so if you do a free body diagram on that mass right in the middle, right? I bet the left one's pulling it to the left, the right one's pulling it to the right. Okay. Which force do you think is bigger? I bet the larger mass is pulling with the stronger gravity force. Right? Guys think? Right. So just a free body diagram on that middle mass. Right? And then the net force, which should be the sum of those two forces. So I'll call this force to the left, force to the right. Right? I'm going to say that the net force, which is again like the sum of the forces, in this case it would be what's the force pulling to the right minus the force pulling to the left. Would that be the case? Right. And then, oh, and you guys know what each of these forces would be. I mean, they're talking about gravitational forces. Let's do universal gravitation. Could you guys do, say, force right minus force left? Got to go universal gravity constant times m times m, so the right mass and the center mass, all divided by, say, half that distance squared, right? Pulling to the right, right? And then left, so I have to subtract as opposite direction. Universal gravity constant, mass left, mass in the center, all divided by also d over 2 squared. Right? That would be the net force right there, wouldn't it be? Right? Bet you guys could figure that out. Okay. Right. And the other question is, well, where would you have to put this central mass so that there was like zero effect? Right? Guys, should I slide it to the right or to the left to get zero gravity? How about to the left? Like closer to the smaller mass, right? Closer to smaller mass, right? Okay. So go ahead and draw that up. So similar type picture. Got the same two masses going on. So mass left, mass right. Okay. And then maybe about, I don't know, just pick a point, maybe like there. Okay. Got the mass in the center. Okay. Ooh, does the value of the mass, the central mass, I think they said 50 kilograms, right? What if you made it more massive or less massive? Would that affect the position it has to go? No, yeah, it has nothing to do, right? Another way to think of it is like gravity fields. There's some place where the gravity field zeroes out, and it doesn't matter how massive the object is that you put there, right? It still zeroes out, right? And so, maybe if the whole thing is some distance d, there might be different ways to set this up and think about it. Right? Sometimes there's multiple ways to set it up. Right? If the whole distance is d, maybe I could define the position as like relative to the left mass. I could call it like x. Right? Would that make this distance right here like d minus x? Is that true? Right. So you got d, got x, and then d minus x. Remember, like solving for x kind of thing. Right? D was given. It's like so many meters. Right? Just we're trying to figure out where we're gonna plot this thing. Right? So it's the same type setup. I'm gonna go net force, which is the sum of forces. Right. That's the let's do like right minus left, or maybe we should draw this, right? Now this time they should be equal magnitude, because that's the point of this, right? So the force to the right and the force to the left are the same magnitude. So let's go force right minus force left. Okay? And that's going to be universal gravity constant m over, okay, so see to the right, if I'm doing right minus left, okay, this is d minus x quantity squared, and then minus, and then to the left I got g mass left. Oh, whoops, I'm so sorry. I got oops. Sorry, I need to amend this. Okay. Mass right times the mass in the center. Oops, because these are the two masses gravitationally attracting. Right. Mass left, mass center, all divided by x squared. Right, okay. And that difference has to be equal to what? Like 0. 0. Right, guess that. Okay. Oh, so they gave you all the values except for x. You guys think you could solve for x? Oh, yeah.
Which one do you put? Yeah, which one do you put first?
Huh?
So do we put those? Like, do we do right or left first? Like, which?
Oh,
do you like the one with the larger mass?
you could do either way. You could do right minus left, left minus right. Either way, it's going to 0 out. Yeah. So here, you can swap these two. It's still 0. Yeah.
Okay.
Yeah. So you can do left minus right. That's all right. All right. Okay. One thing I see is that whatever mass c is, just you could cancel that in anyway. It's the same thing for universal gravity constant. That could be any number. It's still going to give you the same location at the end of the day, right? So g kind of goes away, mc kind of goes away, right? Now we got a proportionality. This is looking like, I bet you could do quadratic, or I bet you could take the square root at some point to like skip past the quadratic, right? To like save you the quadratic, right? But that's the setup. Are you guys okay with the setup? Because the rest is just algebra, right? And you know all these numbers except for x. And that's the question is, what is x? Right? Okay, guys go ahead. Right, next one. Ooh, this one I like a lot. Number 43. Satellite of Mars called Phoebus, right there. I might mispronounce that. Has orbital radius of so many meters and a time period of so many seconds. Okay? Now, it's really nice that they gave you orbital radius. They're talking about the distance from the moon to the center of Mars, right? Sometimes they'll tell you the altitude, like the distance above the surface, but then you have to add the radius of the planet to get the full like orbital radius. But they gave us here. And a lot of times for time period, they'll tell you like you have some number of days or some number of years, and you have to convert to seconds. Here they gave you the number of seconds, which is exactly a number that could feed into your calculator because it's base SI unit. Right? Assuming the orbit is circular, determine the mass of Mars. Yeah, my honor students also had a very similar question. It was like watching a moon orbit Saturn. You guys have a moon orbiting Mars, right? So if astronomers are watching the moon orbit the planet, you know, if they spy like, okay, what's the orbital distance from the center of the planet to the moon, right? They kind of figure that out just by looking through a telescope, right? And then you break out a stopwatch and say like, how much time does it take to go around? There's enough information embedded there to figure out what's the mass of the planet. I mean, you have to know universal gravity constant, but it's all there, right? So here's where I want to prove to you guys Kepler's third law, right? So we're going to go, okay, let me just a little bit fast, right? I'll call it mass of the moon, little m, mass of Mars is big M, and we're solving for that, right? And the orbital distance of going like center to center, I'll call that r. And, okay, so this is orbiting around, right? So the setup starts the same, the setup starts the same way as your, some from your notes yesterday, orbital speed. Isn't the centripetal force being provided by the gravitational force? Or let me switch that. I'll say gravity force is provided by, or is acting as a centripetal force. Let's do universal gravitation, G m over r squared, so from Newton. And then from your lab, that's mv squared over r, right? The m's go, so it doesn't matter the mass of the moon, right? The r's, well, partially, right? Now, yesterday, here's where we branched off and said, just take the square root of both sides to get orbital speed for a circular orbit. Now, here's where we're going to do something a little bit different. Because they said something about time period. Time period, does that have something to do with this v right here? Now, how did you guys calculate time period? Or sorry, how did you guys calculate speed back in your last lab? What did you guys do? Yeah, just divided by time. Like 2 pi r divided by the time to do that. So I'm going to make that substitution right here. So we got gm on r is equal to, and then this is 2 pi r divided by the time period, right? Because circumference, and don't forget to square that, right? Circumference divided by the time period to do that, right? Now, if you multiply this out, this is gm on r equals 2 pi quantity squared, r squared divided by t squared. I'm going to do some cross multiplication here, cross multiply. I'm going to get g m t squared equals 2 pi quantity squared, and then, oh, that r is that r. That's like r cubed, isn't it? Right? Now, right there, that right there, look at what we just showed. Right, so constant, constant, constant. The time period squared is proportional to.
You may or may not have heard that we need to shelter in place for inclement weather. You hold where you are, students return to your class. Everyone stay put for shelter in place for inclement weather. Thank you for your cooperation.
Okay, so hang on here. Here, I'll just take a few minutes here. All right. Look what we just showed, because G is universal gravity constant. Mass of the planet is not changing. 2 pi, that's a constant. Look at this. The time period to go around is going to be proportional to like that average distance cubed. Hey, isn't that exactly what Kepler found empirically by looking through a bunch of data? That's it, right? Again, as far as Kepler got was, so we're hanging out here, right? Was this proportionality, right? And I showed you on this poster, well, I'm making the claim on this poster that if you bring in Newtonian mechanics, supposedly you can update that to make an exact equation, right? Ooh, that should be able to go from here to here, I think, right? Let's see. If you were to solve for time period, it looks like, right? So you could divide the GM over, oh, there's the GM down the bottom. If you take the square root, oh, and there's a square root. And then the 2 pi, well, square root, oh, it just goes 2 pi. Hey, that is that, isn't it? Just a few algebra steps away from each other. Okay, so that right there. And there's a few different versions you can have this in. There's one way to do it. There's another way to do it. I mean, there's a lot of ways you could write that. Right. There's a Kepler's third law right there. Right, now to finish this off, we're saying what's the mass of the planet. Interesting, you can do this, that you can just watch moons orbiting a planet. And it doesn't matter what the mass of the moon is, right? As long as you know how far away it is and how much time it takes to go around, you can in principle solve for mass of what's being orbited, which is planet, right? So last steps are going to be just divide the g and the t squared over. Get some paper for that. Let's do that. So going to divide the g and the t squared over. So that's going to be mass of the planet is, I got a 2 pi quantity squared, got R3, all divided by g t squared. Right, there you go. Right. So there's the solution in terms of variables. Now you can look at any planet with anything orbiting it, and you can figure out exactly how massive it is. Right? Like ideally, you guys should be able to solve this yourselves, right? You could plug in numbers whenever, or you could plug in numbers at the start. You'd still get like the same solution, right? And since you guys are AP, hopefully you guys can solve this in terms of variables. Right? You guys can do it. Solve in terms of variables. Right. All right. Here, I'll go ahead and that's as far as I got my other class. So wrap up that recording right there.